Thanks for coming. I know it's kind of late. Um, if y'all have specific questions, we'll address that. But I thought I'd just sort of go through the chapters, and then if you have questions about the things as they come up, then you can ask. Okay. So let's see. Probably might just get through chapter 7 and 8. We'll see. So chapter 7 was largely kinematics, and you're going to see sort of several types of questions. One is just converting and knowing what the various values are. So remember we had theta here, we had omega, and we had alpha. This is measured in radians. You need to know how to be able to convert from radians to degrees to revolutions. Right? And just remember that 1 revolution is equal to 2 pi radians is equal to 360 degrees. And to convert back and forth, use the conversion factors like we did in chapter 1. We can look at some questions on the exams. We've done them before. I think y'all probably okay, but we'll take a look at it. Omega, remember, is in radians per second. That's our angular speed. And then alpha is radians per second squared. And then these were all related by these equations. Now you have these equations, but you'll need to know how to use them, and we'll work through some sample problems. We have omega equals omega naught plus alpha t, and then theta is omega naught t plus 1/2 alpha t squared. Also, you need to be aware of these relationships. So we've had questions like this before on the concept test, and we'll show you some on the old test. But that omega is proportional to the time, and theta is proportional to the time squared. As you know, I like questions like that, where if I change one variable, how does it affect the other variable? So for example, if I doubled the time, what would that do to theta? It would quadruple it, right? So if I double the time here, then that would have a factor of 4 times the angle of theta. We'll see some questions like that. We've seen some in class, but I'll show you some on the old test. That's really it for chapter 7. There's not a whole lot in chapter 7, so I'd expect fewer questions from that chapter. Let's see, if we're looking at about 27 or so questions, how would that divide up? I would expect maybe 6 questions or 7 questions from chapter 7, and then the remainders from chapter 8 and 9. Okay? Well, let's look at some old test questions, just sort of give you a flavor of what you might see there. I'll just pull all the old tests here. This is last year's test. Yeah, last year's test. Oh, there is one other thing. I did forget this. Let me go back to the notes. There is the centripetal force and the acceleration. Yeah, this is actually a pretty big topic in chapter 7. I'm sorry that I missed it. But if I have an object that's moving around in a circular path, like this, there's a force that's pulling that object into the circular path, and we call that the centripetal force. And the centripetal force is equal to the mass times the centripetal acceleration, and that acceleration is mv squared over r. So the centripetal force is mv squared over r. Let me double check something right quick. That was supposed to be on your equation sheet. Let me make sure it is. Oh, I have it on my mind. So if you go to your equation sheet, it is, no, there it is. Yeah, so the centripetal force is mv squared over r. Okay? Where v is the speed, here v is the speed that this object is going around the circular path, r is the radius, and m is the mass. Right? This is also related to omega, because v is equal to omega times r, so I can say then that this is also m omega squared r. So if instead I'm given omega instead of v, then remember the difference between these. V is a linear velocity, and omega is an angular velocity. Meters per second, radians per second, or revolutions per second, or degrees per second, whichever unit you're using. All right, so those are all measures of my centripetal force. As we discussed in class, the centripetal force is not a separate force. It's just used to describe an already existing force. So for example, if I have this object moving around in a circular path, the centripetal force is provided by the tension. That is if I'm swinging it over my head. Now in this case, the centripetal force is not only the tension, but it's also the what? What other force is acting towards the center of the circle in this? Not the normal. There's no normal force. That's a good guess, but there's no normal force because you need a surface for a normal force. You're on the right track. And you were about to say what? The weight. Okay, so the weight here is also a provider of the centripetal force. So if I imagine here my object at the top, I have two forces acting down. I have the tension in the string, and then I also have the weight. We worked through a couple problems in class, and you have some in your homework, but you can do all the business that we did with Newton's second law here as well. So we could say that the sum of the forces is equal to ma. But here, because we're moving in a circular path, it's equal to ma times mar, which is our centripetal acceleration. Let me put c here, mac. That is to say that the sum of the forces, that's Fw plus Ft, is equal to mv squared over r. That's at the top of the trajectory. I'll do a problem in just a minute when we look at the bottom of the trajectory. Okay. Also wrapped up in this, we did another problem, which we'll see on some of the old tests, where we have a car going around a curve. I always like to get this problem, I don't know why. It's a good problem. Can I go away from here? All right, so if I have, say, a car going around a curve, that's an overview, like looking down above. It has a certain radius of the curve. Now the force that's causing this to go into circular motion is going in this direction. And what is that force provided by? Not gravity, but not tension. There's no rope attached to the car. The frictional force, yeah. So this centripetal force here is provided by the frictional force. Right? So because of this, I can say mv squared over r is equal to the frictional force, which is mu s times the normal force. You recall back to chapter 4 or whatever when we did this, that normal force is equal to the weight. So that's mv squared over r equals mu s times mg. All right, so that was sort of another class of problems dealing with centripetal forces. One other thing, not assume that you know this, but just be aware that if you need to find the speed of an object moving around in a circular path, that's equal to the distance that it travels divided by the time, and the distance that it travels in one revolution is equal to the circumference. So that's 2 pi r over the time to travel one period, which is t, the period. The time to travel one circumference, which is the period. Ooh, this might be on your equation sheet. Let me check. It is not. Okay, yeah, so, oh, it's on your lab equation sheet. That's something you should know. It's just distance over time, which is circumference over the period. Okay? No, this is fast, guys. If I'm going too fast, then please stop me and I can address questions or sort of touch back on some of those issues. But for now, let's go and look at some questions, because I think that that'll be better for the practice. All right. So let's say we've looked at a lot of these in class. I'm going to go to an older test. Okay, so here I have an object at rest, begins to rotate with constant angular acceleration. By the way, guys, this is FO8, exam 3, Fall 08, exam 3. If this object rotates through an angle theta in the time t, what angle does it rotate through in the time 3t? So if I triple my time, what happens to the angle theta? And remember, this goes back to what I was saying before, that theta is proportional to time squared, which just comes from this equation, So theta is proportional to time squared. That's assuming that omega naught is 0, and in this case it is, right, because it's at rest. And so if I triple my time, I multiply by my angle theta by what? 9, right, because 3 squared is 9. So my answer here is B. All right. Number 2 here is a nice just kinematics problem. I would expect a couple from this chapter. As I said, there will probably be about 6 or 7 questions from this chapter. Tire is placed on a balancing machine. It starts from rest and turns through this many revolutions in 1 second before reaching its final angular speed, and I want to know its angular acceleration. Good practice on these problems is to write down everything that you know. Now maybe on the test you wouldn't have to do that. Like you could say, well, it starts from rest, that's my omega naught. This is my theta, this is my time, and I'm looking for alpha. So in a rush, you know, if the test is kind of a rush, you need to really be on top of things, you might do that. But let's sort of go through. I like to write down everything that I know. Omega naught is equal to 0. Theta is equal to 1.59 revolutions. T is equal to 1 second, and I'm looking for alpha. And then I look at my equation sheet, or if you just know those equations, you could probably tell from this that I'm going to be using this equation. Theta equals omega naught T plus 1/2 alpha T squared. Fortunately for us, the omega naught is 0. So this whole term just goes away. Fortunate, because otherwise we'd have to use the quadratic equation, and then that's a whole other thing. All right, so now I want to know alpha. And so I solve this for alpha. That's my angular acceleration. It's also useful for y'all just to be familiar with these equations, that you sort of know what the variables are called and what they are. So that'll come with practice as you go through these kinematics equations, because they're sort of different letters than we're used to dealing with. Okay, we have one other thing to deal with here, and that is these are in radians, but our angle theta is in revolutions, so we'll need to convert that. You'll have to do several conversions on the exam, so make sure that you're okay with that. Questions? Again, going fast, so if I lose you, just stop me, okay? Is that clear? All right, so I have 1.59 revolutions over here on the side. I want to convert that into radians in 1 revolution. There are 2 pi radians. What's that? Almost 2 times 6. I get 10. You know what you get? Yeah, I got 10 radians. All right, so I have 10 radians equals 1/2 of alpha. T was 1 second squared. So that is alpha equal 20. Solving that for alpha, I just divide both sides by 1/2. 10 divided by 1/2 is 20. That is in radians per second squared, and so D is my answer. Be very careful with the units, okay? So since I expect you to know how to convert between these different units, I'll often have things like that in questions. But if you do this without converting it, you get one of these other answers. So please be very careful about that. Just read carefully. Make sure you're reading the units. Expect that. Okay, y'all good with that? Sorta, kinda? Yeah? Maybe? Okay. Yeah, practice is really good, okay guys? Lots of practice will help you. Okay, this is a similar question. It looks sort of like a kinematics problem, but it's not. Okay, so let's just start by writing down everything that I know. And again, if you're with practice, you might just be able to go through and say, well, that's the radius, this is the velocity, this is the time, and now I'm asking for what is the acceleration of the stone. Now, it says that it's traveling at a constant speed, so the angular acceleration of this, which I'm not asking for angular acceleration, I'm asking for the linear acceleration. And the reason I know there's a couple things. First, I don't say angular acceleration. Second, if you notice the units here are in meters per second squared, not radians per second squared. So I'm not looking for an angular quantity, I'm looking for something else. Now, now it's traveling at a constant speed, so I'm not asking for the tangential acceleration. Several different things going on here, right? If I have an object that's traveling around, it has a tangential acceleration that is equal to alpha times r. Remember, those linear and angular quantities are related by the radius. It also has another acceleration. This is what we call the centripetal acceleration. That's in that direction. It's always towards the center of the circle, AR. And that AR is what we're looking for. So AR is our acceleration. It's our centripetal acceleration. And it's equal to v squared over r. So I'm just looking for that. I have 30 meters per second as my speed. That squared divided by r, which is 0.5 meters. That's 900 over a half, which is 1800. All right. You would know this. There are several cues to key you in that this is not a kinematics problem like the previous one, even though it looks really darn similar, right? You sort of have a lot of the same values and a lot of the same words being thrown around. But just to recap, one, you look at the units here. Always pay attention to your units in problems. But the units tell you that I'm not talking about an angular quantity, I'm talking about a linear quantity, that is in meters per second squared. And then also, as I said, when I ask for the acceleration, I don't ask for the angular acceleration, I'm instead asking just for the acceleration. And then actually, you know, there's a lot of things in here that would cue you in that you actually need to find the centripetal acceleration, because you have the speed and then you have the radius as well. The time, however, is not necessary. You don't need that to find the acceleration. That's just sort of extra. Can I clear this, guys? Okay. These are all good questions. I would expect questions similar to this. This is another similar question, but a little bit different, where I have this car going around a curve. All right, I have a frictional force, Fs, and that frictional force provides the centripetal force. In a homework problem like this, Fs is equal to my centripetal force, Fc, that is to say mu Fn is equal to mv squared over r. Since it's on a flat curve, on a flat surface, that normal force is equal to mg. And that's equal to mv squared over r. Dylan? Right. My masses cancel. And I'm looking here for the speed. So that's mu g equals v squared over r. You can solve this how you like. I'm going to cross multiply. Mu gr equals v squared. And then I take the square root of both sides. So v is equal to the square root of mu times g times r. Point 2, 10. The radius is 100. 0.2 times 1,000, 200. Square root of 200 roughly, which is 14. All right, so that's my speed. Alrighty. Remember that if you're on a banked curve, that it's a little bit different. I wouldn't have you work out a problem on a banked curve. It gets a little bit complicated. It's not terribly complicated. Actually, did you have a homework problem on a banked curve? You might have. But nonetheless, I wouldn't have you work a numerical problem on a banked curve, but I could very well ask you a question about sort of what happens on a banked curve. On a banked curve, this is our car, sort of looking at it from the front. You have several forces acting. You have the static frictional force acting in this direction. So that acts as your centripetal force. But then you also have the weight acting in this direction and your normal force acting in this direction. So what happens is you get components of your normal force and your static frictional force. So you get a force here. This is the x component of your normal force, and then also a component of your static frictional force that both act to keep your car on the road, that both act to push your car into this circular path. So in this case, my normal force and my frictional force act as the centripetal force. How's that feel? Is that exciting? It looks exciting. Like on your faces, you look very excited about that. It's good. That's why they build banked curves, so that you can go faster. It allows you to go faster without sliding off the road. Let me clear this. All right, that's getting into chapter 8. Let me look at some of the other tests. I think we're sort of covered all the major questions for those chapters. Any questions about chapter 7, though? We'll look at a couple more and let's see if I have any more. How y'all feel about chapter 7? You don't have any feelings? Like you're not emotional about it at all? I don't really like chapter 7 that much. I don't think there's really that much in it. It's just a few equations, right? Okay. Let's look at some others. Did we look at this one yet? Oh, that one's getting into chapter 8, actually. What? That's chapter 7. Is this one we just looked at? Oh, where's my mouse? Sorry, I lost something here. Oh, let's see, they're all down here. See, we worked this one or something similar to it. That one too. Okay, let's look at this one. So here I have two people on a merry-go-round. One sits on the outside edge and one on the center, or halfway. So I have one person here and then one person here, right? And it's spinning about this axis. I want to know who has the larger centripetal acceleration. All right. I know that this person has a bigger speed, right? But I also know it also has a bigger R, right? Because it's at a larger radius. In fact, I know that V equals omega times R. So if you have a bigger radius, you also have a bigger speed. And so my centripetal acceleration, AC, is equal to V squared over R. So if I have a bigger speed and a bigger R, how does that affect my centripetal acceleration? Well, you probably know this sort of intuitively, that that person on the outer edge will feel a larger velocity, but this equation doesn't necessarily answer that for us, because if my V increases and my R increases, then it's not entirely clear what that will do to the centripetal acceleration. But if I write my centripetal acceleration like this, AC equals omega squared R, I can see that if I have a bigger R, then that gives me a bigger centripetal acceleration. You follow me on that? I don't think that is on the equation sheet. Let me look and see. No, that's not on there. But the relationship between that comes about just by substituting this into here, and I get m omega squared r when I substitute that v equal omega r in for v. Okie dokie. All right, let's look at some more. I know this is fast again, but oops, that's not what I wanted. Okay, let's look down at some others. Right, and that one. Oh, here's one. This is like I talked about before. Which of these reasons is the correct explanation for why it is possible that you can drive at a higher speed? This is my normal force. This is my frictional force. Remember, both of these provide forces, or excuse me, that's my normal force. In this direction, components of those vectors provide forces that provide your centripetal force. And so let's look at the answers here. Which of it is it? Why can you go faster? Oh, what is the answer there? The normal force cars, kind of a flat curve. Yeah, that's not very well worded. I think I might have changed that question, but the right answer here would be C. But a better answer would be just that the frictional force and the normal force both provide a force that acts as a centripetal force. Both provide the centripetal force. Yeah, disregard this question. All right, let's see. Let's go on to Chapter 8. Chapter 8 is sort of the big chapter. Any questions about Chapter 7? Or other things you'd like to dwell on for a while? I mean, this is fast. We'll have another help session next week. I sent out the date for that. I think it was, do y'all remember what day it was? Tuesday, yeah, Tuesday, I think at 1:30. Yeah, I know that might not be convenient for some of y'all, but if you're able to come, that's great, and we'll sort of go over Chapter 9 then. Well, let's look at Chapter 8. Let's see, Chapter 8 dealt with a lot. We had Newton's laws, moment of inertia. Let's do moment of inertia first. Moment of inertia is a measure of how difficult something is to move. So when we're dealing with linear motion, mass was what described how difficult something is to change its state of motion. So something with a lot of mass was difficult to move. Something with not much mass was very easy to move. Here, though, instead, we have moment of inertia. And moment of inertia is defined as the sum of mr squared. All right. We did a discrete particle in class where you had 3 sets of masses, and to find the moment of inertia, you just added up each mass times each moment arm squared. So for example, this is 1 kilogram, 1 meter, 2 kilograms, 2 meters. If I wanted to find the moment of inertia just for those two, I would say 1 times 1 squared plus 2 times 2 squared, and that's equal to 1 plus 8, which is 9 kilogram meter squared. All right, just adding up this sum of mr squared. Notice that my radius is squared, or my moment arm rather is squared. That's the distance from the axis of rotation to where the mass is located. And so if you increase that moment arm, it has a great effect on the moment of inertia. So if I move mass out to large radii, it increases my moment of inertia by a lot. Okay, so we also dealt with the moment of inertia of shapes, and you have a table on your equation sheet. Let me show you. This is the table right here. It has the moment of inertia for regular shapes. You have a cylinder, which is also a disk, like a merry-go-round, for example. You have a cylinder that rotates around an axis through the middle, like going through your hips. And then you also have a thin rod, which is similar, but a thin rod doesn't have a radius. So you could tell the difference between those if I gave them to you on a test. A cylinder, if it was a cylinder that was rotating about its hips, then I would give both its length, which is B, and its radius, which is R. Okay? Versus a rod, it would be a thin rod, like a stick or something, and it would have just a length, a mass and a length. And then I give you the moment of inertia for a solid sphere and a hollow sphere. Okay. You'll need to just be able to be familiar with those and know that they exist on your equation sheet. And then given a problem, which we'll see in just a sec, be able to select the right equation. So given a shape, decide, well, this shape is a hula hoop, so it's, I equal mr squared. Or this shape is a broomstick handle, so it's what? A broom handle is what? A rod, right. And you would tell just sort of by the quantities that I give. Like I said, I give you the length and or the radius if you needed that. All right. So that's moment of inertia. We did have some questions in the concept test, in the online quizzes or in class, where I gave you different objects and you had to figure out what was the moment of inertia or rank them. You could see a problem like that. Those are good problems that sort of test you really understand what moment of inertia is. So for example, in class we had a shape that looked like this, a T, where this length is the same as this length. So I'm taking two identical rods and I'm putting them together like this. And then the moment of inertia can be quite different depending upon the axis of rotation. So let's say I rotate about this axis, that will give a much different axis of rotation than if I go about this axis. Which one would be bigger moment of inertia? About the red axis or about the green axis? The what? The bigger moment of inertia is the one that gives you the most mass at larger radii. So the bigger moment of inertia would be here, where this thing is rotating around, or here, where this thing is rotating around. They would not be equal, because one of them has a lot of mass at a large radius, and that one is the red, yes. The red. Were you saying red before?
Yeah.
I couldn't hear you. You gotta say it with gumption. Yes, red. Okay, so red has a larger moment of inertia because you have a lot of mass far from the axis. And so since it's mr squared, when r is big, that makes the moment of inertia really big. Green has a small moment of inertia because all this mass right here has r equals 0. Right? So if I have mass on the axis of rotation, it does nothing to the moment of inertia. It doesn't contribute at all. There were a couple homework questions on the quiz, the online quiz or the in-class quiz, the concept test, that deal with this. So make sure you sort of understand this idea that if my mass is at large radii, that increases my moment of inertia. All right? So that's moment of inertia. Closely related to that is Newton's second law, which is the sum of the, or actually let's do torques first. Torques are equal to Fr sine of theta. You're going to have just a basic torques problem with one or more torques acting on an object, and then you have to find what is the net torque. So we did a problem in the book where I have this object, let's say it's rotating about this axis, and I have two or more forces acting on it. I have a force here, 2 newtons, I have a force here, 1 newton, and I have a force here, 3 newtons. Let's say this distance is 2 meters, 2 meters, and we'll say this angle is 30 degrees. And I want to know what is the net torque acting on this bar that is rotating about that red dot. Okay. So what is the torque due to this force? That's a question. Not constant. What did you say first? It's nothing. Right. There is no torque due to this force because the angle between the moment arm and the force is 180. Right. So my moment arm is measured along this axis, and my force is in the same direction. So that angle you can think of as either 0 or 180. And since the sine of 0 or 180 is 0, then there's no torque. So imagine if I have an object that's rotating about this axis. If I push in this direction, no torque. It doesn't cause it to rotate at all. Okay? But if I push down, like this force, actually I was rotating about this axis. If I push down like this force, I cause a rotation in the clockwise direction. Okay? What about this force? What kind of torque does it cause? this is a force that's acting right here, and it's pulling up. How does it cause it to rotate? It doesn't. No, it doesn't cause it to rotate at all because it's at the axis of rotation. All right, so a couple things that were there. This one caused the torque equal to 0 because theta was equal to 0. This one caused a torque equal to 0 because R was equal to 0 for that one. And so this force is the only one that causes a torque, and that torque is equal to 6 Newton meters. 3, which is the force, times 2, times the sine of the angle, which is 90, and the sine of 90 is 1. Okay. You will have a problem like that. I'll just give you an object of R or whatever with several forces acting on it. Some of the forces will cause torque, some will not, and you'll need to find what is the net torque. Don't forget, clockwise torques are positive or negative? Negative. Counterclockwise torques are positive. Yeah, this is a clockwise torque, right? I always like to just put my pen here or whatever. I'll use my arm and rotating about this axis. If I pull down here, it causes it to move in that direction. But you can just take your pencil or whatever, like this. And if I pull down, that causes clockwise rotation. All right? No rotation at all, no rotation at all. Yep. No, not the sine of 30.
Sorry, I missed that.
Yeah, I'm sorry, I'm talking kind of fast. Here, I forget your name, I'm sorry. Ashley. Okay, Ashley, yeah, so the angle here is 90 degrees. I don't say that, but you should be able to look at it and see that it's 90 degrees. And torque is equal to F times R times the sine of theta. The force is 3 newtons. R is 2 meters. And the sine of 90 is equal to 1. So it's just 3 times 2. This one didn't come in at all because that torque was 0. Here I have 0 torque due to this force because the force is acting at the axis of rotation. So R is equal to 0 in this case. All right. Okay, so you have a question like that. Probably just one, maybe 2. All right. Can I go down from here?
So from the force from the actual,
What's that like?
force and the actual object that you're talking about, that's when you change
I didn't catch those last 4 words. That's what you're aiming for. Is that what you said?
Yeah, the force and your angle, that's what you, force and the object, that's what you change from that.
Right.
That's like at the 90 degree.
Right. The angle between the force and the bar, the object. It's really the angle between the force and the moment arm, which is really a vector, but the moment arm is always along the object for our purposes. All right. All right. That answer your question? You guess? Okay. All right. Let's look at another question. So we'll also see some Newton's laws. Newton's laws is torque equals I times alpha. The sum of the torques equals I times alpha. We worked through several problems like this. You had some in your homework. Could give you, we'll look at some tests and I'll show you some example questions, but let's take that bar. Let's say that bar, we've already found that bar rotating about this axis has a net torque equal to -6 Newton meters. Remember, it had a 3 Newton force at 2 meters. 3 times 2 is 6. And negative because it's clockwise. Right? Clockwise torques are negative. And so we've already found that the net torque of that is 6 Newton meters. Now let's say that the mass of this thing is 3 kilograms. And I just want to know what is the angular acceleration. All right, I would go and look at that equation sheet, and I would say, well, shoot, which one of these do I use for this rod that's rotating, or excuse me, this bar that's rotating? Which one do I use? Right, I use the rod, which has a moment of inertia of 1/12 mb squared. And then I go back to my question, and I would say, well, I is equal to 1/12 mb squared. That's 1/12 of m, which is 3 kilograms, times the length of the bar, which is 4 meters. That's 1/12 of 3 times 4 is 1 times 4. So that's 4 kilogram meters squared. Isn't that right, Lindsay? Yeah. All right, so 4 kilogram meters squared. And then if I want to know alpha, I just say the sum of the torques equals I alpha. That's from here. That's Newton's second law. So alpha equals the torques over I. The sum of the torques was -6 Newton meters over 4. So that's 1.5 3/2 radians per second squared. You will see one or two, probably a couple of these. These are pretty important. They sort of bring together our moments of inertia and then our Newton's second law. And then in addition to that, you could also see an additional kinematics question. So I could ask, well, after 3 seconds, what is the speed? And then you would have to go back to those kinematics equations. Let me show you that for example. So let's say I did ask that. I said, well, after 3 seconds, what is the speed? At t equals 3 seconds, I know that omega equals omega naught plus alpha t. If it started at rest, that would be 0. And so I'd have -1.5 radians per second squared times 3 seconds, which is -4.5 radians per second. So several steps in that. I had to find the net torque, which we found in the previous problem. That's just adding up all the torques. Find the moment of inertia, in which case you have to use that table to find the right shape. Find the angular acceleration. This is Newton's second law. F equals ma, torque equals I alpha. And it's -1.5. That'd be torque over my moment of inertia, -1.5. And then solve now for the angular speed. Or I could ask you the angular position. But in those kinematics questions, you know, in the chapter 2 and 3 tests, which dealt with kinematics, you had to do some systems of equations. You're not going to have to do that here. It'll be all pretty straight. You're not going to have to solve one equation for one variable and plug it into another equation. You remember doing that? Yeah. Not going to have to do that. It'll be more straightforward. You'll have all your knowns, what have you. All right, so find this, and that would be your answer. Although the answer would be listed like that, it would be 4.5 radians per second in the, what is that, clockwise or counterclockwise? That's clockwise, right? Because clockwise is negative. So the answer would actually say 4.5 radians per second in the clockwise direction. It wouldn't list the negative. So remember, the negative just means clockwise. It's sort of a direction. It's not really a direction. It's just sort of what a rotation direction, if you want to think of it that way. All right. I know this is fast, guys, but is this okay? We doing okay? This is a good review for y'all? Okay, I'm not done yet, but if y'all need to go, I understand. Because there are a couple more topics in this chapter. We had angular momentum and rotational kinetic energy and the work energy theorem. Let's do energy first. The kinetic energy before was 1/2 mv squared, but now we're replacing our m with moment of inertia and our v with angular speed. So now our kinetic energy is 1/2 I omega squared. And then we worked a problem like this in the notes, but our work is equal to our change in energy. So if we want to change the energy of an object, we have to do work on it. And the problem we did in class, which could be similar like what you see on the test, and you had, you had a slightly different problem in your homework. Well, you might have had a question like this, I forget. But anyway, if you wanted to stop a rotating object, you have to do the same amount of work as what its energy is. So let's say that we have the object that we had before, say where our moment of inertia was, what was our moment of inertia? Was 4 kilogram meters squared. And it's rotating at a certain rate. What was it? 4.5 radians per second. And I just want to know how much energy is required to stop it. Right? The amount of work required to stop it is equal to its kinetic energy. So I would just calculate its kinetic energy, 1/2 I omega squared, which is 1/2 of 4. That's 4.5 squared. It's approximately 50. What is it, Lindsay? A second, Helen. 40? Alright, so we'll just call it 40 radians per second. Or excuse me, 40 joules. Alright, so I would ask for the work, and you would have to know, well, the work is equal to the kinetic energy, and then you could calculate that work. Dylan?
Yes, sir. I was fixing something on my paper, and I didn't quite catch the values. Will those be given, or do we have to do that?
Well, this is from the previous problem. No, they would not be given. I would say you have a solid sphere of mass, blah, 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 radius, blah, 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 and it's rotating at this rate. How much energy is required to stop it? Or how much work is required to stop it?
So we will have to find I.
All the stuff like we did before. Yeah, you'd have to go to the table, or if it's a set of discrete particles, add up that mr squared for each individual particle. You know what I'm saying when I'm talking about that? How we have these regular shapes and then these discrete particles. You know what I'm talking about? Okay, well, the discrete particles, we did this, where if I have these separate particles that are all rotating at a certain rate, I can add up their moments of inertia, mr squared, and then that will give me their total moments of inertia. Or if I have, you know, a cylinder that's rotating, then I can find its moment of inertia is 1/2 mr squared. Both of those are finding the moments of inertia, but the table actually uses calculus to determine what is the expression for the moment of inertia for those objects. That answer your question, Dylan?
And yes, sir. We would have to do that.
Yes, you would have to find the moment of inertia, yeah.
Why would 4.5 bigger in this situation?
Well,
We used stuff from the previous question.
it doesn't really matter in this case because I'm just looking for energy, and energy is a scalar quantity, and it's squared. That was about the next words out of my mouth. Right, so since it's squared, I didn't even carry that negative. Alright, because the negative goes away. Alright, and then the last thing in this chapter, after this we'll look at some old questions, but in the last thing in this chapter was angular momentum. Angular momentum, which we call L, it's a vector quantity, is equal to I times omega. Remember, this is like the linear momentum, which was a product of mass and velocity, but now we're dealing with, instead of mass, which is a measure of inertia, we're dealing with moment of inertia, and instead of velocity, we're dealing with angular velocity. Alright, so wrapped up in this, and the problems that you'll see have to do with the conservation of angular momentum, that is that Li is equal to Lf. You had a couple homework problems on this where you have objects that are changing their angular, they're changing their moment of inertia, and when you change your moment of inertia, it changes your speed. Remember we dealt with the figure skater, they bring their arms in, and it causes them to spin a lot faster because they're decreasing their moment of inertia. So I initial, omega initial, is equal to I final, omega final. So for example, if I decrease my moment of inertia, I increase my angular speed. That's like the figure skater pulling her arms in, decreases her moment of inertia, makes her spin faster. There are other ways I can change my moment of inertia. Like for example, let's say that I have a disk. This is a disk. It's rotating at a speed of, say, 2 revolutions per second, and it has a mass equal to 2 kilograms and a radius equal to 2 meters. Right. The moment of inertia then for this disk, which is really just a cylinder, is 1/2 mr squared. That's 1/2 of 2 kilograms times 2 meters squared That's 1 times 4, 4 kilogram meter squared. All right. That's my disk. It's rotating at 2 revolutions per second. Now let's say that I bring, I don't know, let's say that I put a bar on this disk. I have it, say it's a flywheel and it's spinning, and then I bring another object and I engage it on the same shaft. You follow what I'm saying? I have a flywheel spinning on a shaft, and then let's say I bring a bar and I engage it on that same shaft by a system of gears, or however it is that I'm doing it. So basically what I'm doing is I'm taking a bar and attaching it to that shaft. And then I want to know what is the new angular speed. So first I need to find out what is the moment of inertia for that bar. I'm just going to use the one that I had before. What was that bar that I used? Oh, it was this 4 kilogram meter squared. Let's say that the moment of inertia of that is 4 kilogram meters squared. I would give you the mass and the length, 1/12 mv squared, would give me 4 kilogram meters squared. And then I want to know what is the new angular speed. And I would take this, I would say I initial, omega initial, plus I final, omega final. I initial is this quantity, 4 kilogram meters squared, times omega initial, which is this quantity, 2 revolutions per second. What is I final? What is my new moment of inertia after I bring this bar and put it onto this disk? It's 8, right, because I have now this moment of inertia and this moment of inertia. So my new moment of inertia is 4 plus 4, which is 8, times omega final. And now my new angular speed, it was 2 revolutions per second. My new angular speed is going to be what? It's going to be 1 revolution per second. That's right. It slows down. My moment of inertia increases by a factor of 2. My angular speed decreases by a factor of 2. That's a nice problem. I mean, that's sort of how they design these systems, these big systems where they have flywheels and gears that are all engaging with one another, because you have to know how fast they're going to go. Hey Dylan, have a good day, okay? Another help session, I'll send an email. Okay, well, come see me if you need help. Okay, let's take a few minutes and just, we're not going to work through them, but I just want to show you some of the problems that are like these that we've worked. Nathan, you have a question?
I think he's more telling calculus.
Okay, if y'all need to go, you're welcome to go. Okay. Class starts at 5?
Yeah, that's fine. Thank you. Plus, I forgot my hat and watch.
Oh, okay. Well, it's a good thing you came back. All right, let's look at those old tests. Okay, there's one where you're just finding the net torque. That's just like, or very similar to what we worked before. Actually, that's very similar. So the only torque, if you're rotating about point C, the only torque is provided by that force. And then you had to find the angular acceleration. Given the torque, find the moment of inertia, and then find the angular acceleration. So that's very similar to what we had before. Here's one, finding the moment of inertia. What kind of shape would you use to find this moment of inertia? Not a cylinder, no. Not a sphere. Not a rod. Not a disk. Use just the discrete particles, right? The sum of mr squared. You know, if you have more than a couple particles, well, the reason I know this is because I call them particles. I don't call them spheres or shapes of any kind. And so to find the moment of inertia, I would just say the sum of mr squared. I'm sorry? That doesn't matter, no. They're rotated around. I could put them all on one side, but they're all a certain distance from the axis of rotation. 1 meter, 1 meter, and 2 meters. No, you'd say 1 kilogram times 1 meter squared plus 1 times 1 meter squared plus 4 times 2 meters squared. There's 1 plus 1, which is 2, plus 16, which is 18. Right.
So we could never get a negative from that unless you gave us a negative.
Moment of inertia can't be negative, right? Math can't be negative, can it? It's the same thing. You could have 0 moment of inertia, but you can't have a negative moment of inertia. All right? I don't think I would ever give you a negative option. All right, let's see. This is just a torques problem. You have to do the sum of the torques. Here you actually have 2 forces. You have this force right here, which is acting at this distance, and then you have this force here, which is acting at this distance. So you have to add up those torques. Moments of inertia. This is a kinetic energy problem, so you have to find the moment of inertia. Actually, I'll give it to you there. And, oh, it gives you the torque, and then 8 seconds later, so from the moment of inertia and the torque, you can find alpha. And then from that, you can find omega, which is equal to alpha t. Here's my t. And then once you get omega, you find the kinetic energy. 1/2 I omega squared. I would fully expect to have questions like that that take several steps. So be careful when you're working through them, because if you get one step wrong, then it messes up your other steps. So be careful on that. So that's a Newton's second law. Or no, the energy, where's the angular momentum? Shoot, I don't see any angular momentum. Okay, yeah, this one's like an angular momentum problem. We'll make this the last one. I have a 1 kilogram ball. It's attached to a spring of 2 meters long. That means that my moment of inertia is mr squared. That's 1 kilogram times 2 meters squared. This is just a ball that's on a string. It's going around in a circle. So it's just a particle, basically, going around an axis. So that's equal to 4 kilogram meters squared. And then the string is lengthened, it says, to 4 meters. So that's now 1 kilogram times 4 meters squared, which is 16 kilogram meters squared. All right, so I've increased my moment of inertia, and I know that I omega has to be constant. So if I goes up, that means omega goes down. I went up by a factor of 4. That means omega has to go down by a factor of 4. My angular speed was 4. What's my new angular speed going to be? 1 is right. Right, so D is the right answer. All right, that's chapter 7 and 8. I think we'll probably stop there. I'm zonked. I'm sure y'all are zonked. I know. Okay, so my angular momentum is constant. That means the product of I and omega is constant. So here, my I initial was 4 kilogram meters squared. My I final is 16 kilogram meters squared. That means my I has increased by a factor of 4. That means omega has to decrease also by a factor of 4. And omega was 4 revolutions per second, so now it has to be 1 revolution per second.
But 4 minus 4 is 0.
4 minus 4? It's not decreasing by 4, it's decreasing by a factor of 4. That means you're multiplying it by 1/4. All right, and you're not subtracting it, you're multiplying it. All right, guys, because I know that's a lot. There's a lot in this chapter. I mean, that's a couple major chapters that cover practically the whole semester. But a lot of the questions are sort of straightforward. Like, there's not a whole lot of variety in how you'll see them, some of the numerical questions. So that's good. That's in your favor. But against your favor is just there's a lot of material. So we'll have another help session. We might touch on this stuff again on Tuesday, but we'll also do chapter 9 on Tuesday. There's a lot there too. But again, it's pretty straightforward stuff, right? It's just if you know the equations and you sort of know how they work, then you can do well in chapter 9. Students often do well in chapter 9 material. I'm here to help too, okay? So this, for some students, this is an important exam, and I'm here to help you with that, okay? So if you want to try to come see me in my office for more one-on-one help, I'm certainly available for that, okay? That's my job, so let me do it.
Okay. I'll see y'all later. Have a good day.
I'm gonna go home. Is this was helpful? Alright, I'll post it online. And if y'all are available, come next Tuesday, but I'll post it online as well.